Okay, so this is QLeadFinder. My name's Stu. I've worked in drug development and discovery for 15 years or so, and quantum is kind of like the next extension of the AI based drug development and discovery. So this is a QLeadFinder, a quantum enhanced lead discovery for drug R&D, and it's using some of the concepts we used in the little tutorial with the qubits. And so the general problem that I'm trying to solve is um, historically, drug discovery depends on similarity searching, which has been done with Tanimoto or other similarity methods in the past. These are kind of 2D to 3D representations, but they don't quite capture all of the similarities that could be inherent in one drug and another. And if you've got one drug that works, but it might have side effects that are undesirable, you want to find similar chemical compounds that are similar, have a similar effect, but might have different or fewer side effects. You want to use the similarity searching to try to parse out some options with drugs you can develop. So what this does is it takes a smile string. For anybody who is not in chemistry, a smile string is basically like a string of characters that represents a 3D chemical structure. So you can take like caffeine or acetaminophen or whatever it might be and represent that in a 2D string. When you do that, you're losing some of the kind of dynamics of the molecule. But needless to say, there's a huge chemical database called Chembl that has like 2.5 million compounds, but searching that is super time intensive. And the similarity searches that have been done for the last like 60 years using Tanimoto's searches, Tanimoto's similarities, don't always parse out the nuances between like one molecule and the next. So using the classical fingerprint, which is like the Tanimoto that I mentioned before, you're basically taking a binary vector, converting it to kind of like a matching features. So say you have eight features or 10 features. You're kind of counting the features that line up as a measure of the similarity. With a quantum kernel, you're doing it slightly differently in that the features are encoded as qubit rotations. This leads to a much bigger feature space that you can kind of explore and see where the similarities overlap and where the new possibilities for um, exploration are. So, who here likes caffeine? All right, a few takers. Thanks for the involvement. So, say we're putting in caffeine as that's the smile string that you've got there. You input it into the QLeadFinder, and what you get is actually I'm going to increase this or decrease this similarity a little bit so we get more options. There's a few parameters that you can adjust, but basically what you get is your Tanimoto similarity, which is kind of like the old way of measuring. And if you get Tanimoto similarities that rank the compounds in a certain kind of order, you'd probably explore those in that given order. But if you explore it in quantum similarity, that gives a different like kind of ranking because it's a much richer feature space, and that can tease out, let's say, a molecule that has a similar effect, but maybe a different structure, and you can kind of find possibilities in potential new drugs that way. So some of the options here are like theophylline. That's like a T compound, like similar compound in T that you might find. But that's it. This goes quick. Thank you guys so much for listening. If you want to connect with me on LinkedIn, here it is. 1 second. And that's it.
Is that use cryptomeet.com?
Yeah, I'll just put this. There you go. So you can scan it and connect with me if you want. But yeah, it's used for drug development and discovery. So that's basically it. Thanks, guys.
Any questions?
Yeah, question.
So what was the coolest similarity you found based on what you just read?
That they're ranked differently.
So was there any like surprising drugs that you saw based on the different ranking?
There was similarities. So the old ranking was kind of as expected,
Yeah.
but the only surprise that I got was that the new ranking was different.
Oh.
Yeah, so I mean, it just gave a different kind of sequence of order of ways to explore potential new compounds. Yeah, yeah.
So yeah, then you were starting with like an initial list of like here's compounds to analyze. It's not analyzing the entire compound space, I assume. Then that means like it's not finding like a novel compound that would act similarly to caffeine.
Great question. So I don't think I mentioned that. So the Chemical database has 2.5 million compounds. It searches similarities based on the old method, ranks the top 50, and then out of those top 50, uses the quantum space to re-rank them.
Okay.
So these are compounds that are known to be very similar, but this is a different way of ranking them and exploring kind of similar efficacy and things like that.
I've heard some like limitations of, like the recruiting method in terms of like I guess coding molecular information. Like, do you have any other features that you consider adding, to get better?
Other features or more features?
Yeah, like maybe like molecular weight in addition to.
That was actually one of the features. Yeah.
Okay.
Yeah, so I had 8 features as samples. That was one of the features. The others were pretty common measures of physiochemical properties. Yeah. So thanks. Appreciate it, guys.
All right. Thanks.